Welcome back. This is the second lecture from our first unit, and we are continuing with scientific notation. What I wanted to review were a couple of different math functions that involve scientific notation. So if you look at the first one, you are adding with scientific notation, and you can see that the first value has an exponent of 2, and the second one has an exponent of 3. So how to deal with this? You can't just add these together and add the exponents. It's not going to be like times 10 to the 5th. What you have to do is make both exponents the same. So my choice was to use the 3.4. What you do is move that decimal place back 1, so this becomes 0.34 times 10 to the 3rd. And then you can add them together. So it'd be 0.34 plus 4.57. And that value is 4.91. And your exponents are now the same, so then it's times 10 to the 3rd. So one more time, the answer is 4.91 times 10 to the 3rd. So hopefully you are trying this with me and making sure that you are getting the right answers. Now, I think that multiplication and division are a little bit easier because during these functions, you really do just add or subtract the exponents. So this second value, or this second problem, you will take 2.00 times 4.00, which is just 8.00, and then 10 to the 3 and 10 to the 4th, you just add them up. So your final answer, 8.00 times 10 to the 7th. When you divide with scientific notation, you will divide your two numbers, 9.60 divided by 1.60, which comes out to 6. And your 10 to the 7th and 10 to the 4th, you just subtract them. So your final answer, 6.00 times 10 to the 3rd. So these are three different ways to deal with scientific notation. If you were subtracting, it's the same rule for addition. All right, so we're going to move on to our units. And units are the part of the measurement that tells us what scale or standard you are using to tell me your results. We have two common systems. We have the English system, which is what we use in the United States, and then you have the metric system, which most of the rest of the world uses, and it's what we'll be using in chemistry class. So this is what we prefer in science because most people around the world that study science are using this, and it became official in 1960. So the metric measurements have been around for a long time, like the meter and the liter and so forth, but the system became finalized in 1960. Why the United States has chosen not to be a part of the metric system, I'm not quite sure. I do know during the Carter administration around 1980, they tried to move to the metric system, and if you look at like a can of soda or a gallon of milk, like the gallon of milk will say gallons, but it will also say milliliter on there. Your can of soda will say milliliter, but also ounces. So you kind of get both units there, but still most people are comfortable with English here in the United States. All right, so your common units for the metric system are, for mass, it is the kilogram, although in lab you'll focus mostly on the gram because that's the type of scale that we have. Length is the meter, so that's your distance, long distance, and we do have meter sticks that we'll measure with. Time is the second. Temperature, this is a new one for you. We will deal with Celsius in our thermometers and also our lab quests, but later you will have to convert to the Kelvin scale because he deals with absolute value, absolute zero. Volume is the liter, which is the amount of space occupied by a liquid, but if you're dealing with the volume of a solid, this is where you'd have to take the length, width, and height and use centimeters cubed. And you will be having a lab that involves volume and some of these other units to help you understand that better. All right, so when you're dealing with numbers in the lab, not only do you have to make them concise, but you have to make them certain. So there is a degree of uncertainty you'll have to estimate based on whatever instrument you are using, and there are rules that follow this. So this is what we call significant figures, and significant really means that you used a scale to find those numbers. It doesn't mean they're more important or less important, it's just how you took that measurement. And some of these will make sense and some of these will not, but as you use these over the course of the year, they'll just become habit for you. So let's go through these rules. Okay, Any number that's not a 0, this is the easiest rule in the book. If it's not a 0, it's considered significant. And significant, again, means that you were basing it on some scale or some piece of equipment that you took the measurement from. So in this number, 1457, there would be 4 significant figures. Leading zeros. These are numbers in zeros in front of a number, and they indicate position. So if you take a look at this number right here, 0.0025, it's the 2 and the 5 that you got from the scale or from the instrument that you were measuring, and these right here just tell you the position, or like how big or small that number is. We're not going to change the value of this number, it's just telling you how much you used from a piece of equipment. So in this case, the zeros in front, the 0 and then the 2 after the decimal, are considered not significant. They're not from a scale or piece of equipment. So here, only 2 numbers are significant, the 2 and the 5. Now, does that mean you are just not including them? No. What happens is, if you are not comfortable with that, you can always write that value in scientific notation, because here it is. Here's the 2 and the 5, right? 2.5. And these 3 zeros become part of an exponent. So when you're dealing with scientific notation, it's the same rule. That 10 to the third does not count. It's not considered significant. So the 2.5 is all you have to deal with. So again, only 2 significant figures. So these 2 values are equivalent, and you can see they have the same amount of significant figures. All right, captive zeros, you can call it captive. I like to call it sandwich because they're squished in between non-zero numbers. So if you look at 1.008, you have 2 zeros in there, right? Because a number is in front and behind those 2 zeros, everything counts. So 4 significant figures. All right, it's the trailing zeros that are the toughest. So if you look at these numbers, they're actually all the same number. It's 100, 100 with a decimal, and then 1.00 times 10 to the second. So 3 different ways to write the same number. So what I'd like to tell you is, in that first value, 100, only one of those is considered significant, and it's the 1. So if you have something like 100 and there's no decimal, or it's not written in scientific notation, only the 1 is considered significant. Okay, now if you don't like to write it that way, then put a decimal. As soon as you put that decimal point, all 3 count. So that's 3 significant figures. Or you can put it in scientific notation, and it's the same deal. That 1 counts, then you have a decimal, and the zeros are after a decimal, after a number, so all 3 count. You do not consider the exponent. So that's pretty tough, and that's why I gave you some practice on this for your homework. Exact numbers means that you didn't use any measuring device to get these numbers, so the rules of scientific notation do not apply. So 8 molecules, 5 apples, telling me that there's 1 inch is equal to 2.54 centimeters. That's just a comparison. None of these were measurements, so the rules do not apply. All right, so in class, I did ask you to try these, so if you're listening to this for the first time, go ahead and pause it and see if you can try these by yourself, and then you can unpause it to hear the answers. So in letter A, there are 3 significant figures. The leading zeros do not count, the sandwich one does. In letter B, 5 significant figures. The 3 leading zeros do not count, the 2 sandwich ones do count, and this 0 counts because it's after numbers after a decimal. Letter C, all 4 count. You do not count the exponent, and this does say feet, and how come over here I said that, when you have these units like this, that it doesn't count? This is an actual comparison. This right here means that you actually measured just feet, so you probably had some yardstick or meter stick out, and you actually did take a measurement. So that's why this will have significant figures, and there are 4. 110 riders in a race, that's just people in a race, so no significant figures. Letter E, 1 and 00 do count, so that's 3 significant figures. The others are just leading zeros. Letter F, again, that's liter, so you could have used a graduated cylinder or a beaker to measure this. So the 2 The 0, the 8, and those zeros count. This is a sandwich 0. These are zeros after a number after a decimal, so there you have 5. 480 Corvettes. Corvettes are cars. You do not measure them, so no significant figures. All right, rounding. So not only do you have to write things concisely and figure out significant figures, you have to know how to round in order to make your numbers concise. Okay, so there's 2 rules. If a digit is less than 5 and you're trying to round, then you'll make no change. So if you take 1.33 and try to round it to 2 significant figures, so 2 significant figures is the 1 and the 3. This 3 is less than 5, so you just leave it alone. It becomes 1.3. If it's over 5, you will increase the number by 1. So if you have 1.36 and you're trying to round it to 2 significant figures, this becomes 1.4 because the 6 rounds it up. Now it becomes a little tricky when you have a series of numbers. So here you have 5 digits and I'd like this rounded to 3. So the way it works is, the 6 has to be there, the 8 has to be there, and this 3 has to be there. But do you round up or not? The question is this like a domino effect, or do you just deal with the number next to it? And the answer is, it is not a domino effect. The 7 does not affect the 4 in this rounding. It is just the 4 affecting the 3. So since 4 is less than 5, this is just 6.83. All right, a couple other functions here. When you multiply and divide your significant figures, one particular rule applies. So if you were to put this into your calculator, 4.56 times 1.4, your answer is 6.384. Now, how do you reduce that to the correct number of significant figures? So for multiplication and division, you count the significant figures. 4.56 has 3 significant figures. 1.4 has 2. So your answer needs to have 2. So you round 6.384 to 6.4. Next one, and this is a perfect example of why you need significant figures. 8.315 divided by 298. If you plug that into your calculator, you get 0.0279026. That's as far as my little calculator got. Now, how do you write that in correct significant figures? You have 4 significant figures in the first value, 3 in your second value, so your answer should have 3. Now, to round this decimal to 3 significant figures, it becomes 0.0279. The 2 leading zeros do not count. Now, the funny thing is, for adding and subtracting, it's a completely different rule, and it's here that you will make the most mistakes because you're just not used to this. This reminds me of like grade school adding and subtracting, where you like line up the columns, because you'll need to understand decimal places for these guys. All right, so for adding and subtracting, it is a different rule. Are you ready? If you plug 12.11 plus 18.0 plus 1.013 into your calculator, you get 31.123. Now, how do you write that in correct significant figures? Look at your decimal places. 12.11, 2 decimal places. 18.0, 1 decimal place. 1.013, 3 decimal places. The least amount of decimal places is here. There's only 1, so your answer should be rounded to 31.1. When you subtract, same rule. 0.6875 minus 0.1 gets you 0.5875 in the calculator. Check your decimal places. Here you have 4, here you have 1. Your answer should have 1. And now you're going to have to round. So you want 1 decimal place, which means you're looking at that 0.5. The number after 0.5 is 8, which means you round up, and it becomes 0.6.